So the slides are originated from my attempt to understand three-body physics at two-body threshold. And while putting the slides, I actually figured out that I still don't have a complete picture. So my talk will be rather a set of questions that I would like to answer and set of answers that I already have. And yeah, so I'm Artem Volosniev, and my collaborators from Aarhus University, Dmitry Fedorov, Axel Jensen, and Nikolai Ziner. And Nikolai Ziner gave here talk last week. And we have two, so basically all the slides are based on one paper and one preprint. And yeah, if you are interested in that, you can find it on archive. Okay, and here's the outline of my talk. So yeah, first I will introduce the system that I would like to work with. Then I'll try to motivate briefly why I'm interested in such a system. Then, as you see, I have a lot of preliminaries. And so I will just introduce some basic ideas or something that is already known. And then I will tell about my results in three bosons, or our results for three bosons, three spinless fermions. After that, I will summarize and give a small outlook.
By spinless fermion, you just mean distinguishable because you have projections?
Yeah, so three spinless fermions basically means that special wave function should be anti-symmetrized completely. So you can think about the spin polarized fermions. So this is a kind of concept, yeah, which basically means that your special wave function should be anti-symmetrized whenever you exchange two particles. Okay? Yeah, but it's like they're identical. So if you have electrons, they're still identical, but they have kind of spin degree of freedom. But if you put them in an external field to separate different spins, then inside of one cloud you have kind of spinless fermions. Yeah, and that's something that I will be talking about. And yeah, so my system, as I said, is three identical particles that live on a plane, and they have the same interaction, and they have the same masses. And as I said, bosons are the particles that are described by the wave function that is symmetric with respect to exchange two particles, and spinless fermions, the wave function is anti-symmetric when you exchange two particles. And yeah, so there's the standard Hamiltonian, of course, and what is different from system to system is an interaction. And here I briefly describe my potential. So that's a standard mathematical trick. So you divide your potential into two pieces, where G is a constant that defines the strength of the potential of the interaction, and V is some function that describes the geometry. And for our examples that I will present, I assume that V is a bounded function of short range. And when I say short range, I adopt Sebastian from Sebastian talk, this definition. And then I assume that the constant G is larger than 0, and it can be tuned somehow. And if for some value G, so when you tune G and you change two-body binding energy, or you change two-body scattering length, and then when G is equal to G2, you don't have two-body bound states. And what we will be interested in is in three-body systems precisely at this point, when G is the same as G2, and if the three-body system at this two-body threshold has a bound state, we will call it Borromean, and that's something that we're interested. So we're interested in a configuration where two-body is not bound and three-body is bound. And this is kind of a pictorial way of thinking about it. So yeah, so we will be interested when G is exactly at G2, for example, but also when G is below. And if for some G which is smaller than G2, you have three-body bound state, you also call it Borromean. You're right. Okay, and now I come to my motivation. So first motivation comes from 3D, and yeah, this is our famous Efimov scenario. And so when you tune a three-dimensional scattering lens to infinity, you get infinitely many bound states. And this is a famous plot. When you tune two-body scattering lens to 0, you get infinite amount of three-body states. Of course, I don't have it here infinity, but and they're all out of scale. But that's the idea. So you have many states, and in a potential picture, it would mean that when you tune G to this G2 to eliminate two-body bound states, you get infinitely many three-body Borromean states, and they survive for some time when you tune A to the positive side, to the negative side. And this scenario was observed in cold atomic gases, but even before you could see that you can have Borromean structures in nuclear physics when you, for example, in helium-6, you describe as alpha particle core, and then you have 2 neutrons, and then because helium-5 is unbound, you have Borromean state. Okay, so that was our motivation from 3D, and now a bit motivation and aims. So what we would like to do, we would like to understand occurrence conditions for Borromean states in 2 dimensions, and then we also, so I personally, when I started, I just wanted to understand why Borromean states occur, and also in 1D, 2D, 3D, so just what is the mechanism. And yeah, and also I would like to understand super Efimov states using real space, and I will tell about super Efimov states later, but we already had a talk from Sergei Moroz, who tell us about it. And yeah, all our theoretical understanding, some we can derive from Hamiltonian, but unfortunately we quite usually need to provide some numerical analysis because Borromean states are not universal. And so what we would like to do, we'd like also to produce a set of numerical examples, and for different potentials. So we'd like to take different potentials, tune G to G2 and see whether there exists a three-body bound state or not, and establish properties of this Borromean state. Then we would like to establish reference points for future numerical computations and test different numerical techniques. And here is, I would say, a bit speculative at this point motivation. So first, you can realize quasi-2-dimensional setups in current experiments with cold atomic gases, basically by applying propagating lasers and cooling your system down such that you confine your particles to quasi-2-dimensional geometries. And few-body physics, even though that usually many-body physics, you have some few-body physics involved. For example, you can see few-body recombination laws, and then you can think about many-body physics. It's something that also Sergei mentioned, that if you have three-body state, three-body bound state, then you can think about matter of trimers that actually at the end might be stabilized for spinless fermions, because you know that when you have Efimov trimers, then you usually enhance the laws. But because you have two-dimensional setup and the spinless fermions, because of the Pauli statistics, you might be able to stabilize at the end of the day. But yeah, it's still, I would say that this is a bit speculative. And to actually give some meaning to our few-body results in this many-body context, we need to take into account quasi-2-dimensional geometries and few-body calculations and few-body calculations for laws. And we also need to take into account for example, Fermi statistics with or Fermi C for spinless fermions. Okay, and now I come actually to main part of my talk, and I will start with just two bosons in 2 dimensions and show that even at this point 3D and 2D are very different. So when we consider dimensionless equation for 2-body bound states in attractive square well potential, so you use as a geometry, you use this potential, you already at this point can see that when you match, so you have 2 solutions inside of your attractive well and outside, and you have 2 solutions, and when you match those solutions from outside and inside, you actually get an equation that can be satisfied for any coupling or for any strength G. And yeah, it's written here. So this is your equation. Basically, you match logarithmic derivatives from both sides to get an equation for binding energy. And when G goes to 0, you actually can simplify or tail expand from both sides. And then you would get that it's not a tail expansion. So use asymptotic decompositions. You would get such an equation. And from this, you would see that the binding energy actually scales exponentially with the strength of the potential, but still you can satisfy even for really small value of the strength of the potential. And at this point, you actually see that numerically it's not that easy to work with such systems because they will have really small binding energy compared to the strength of the potential when the strength goes to 0. Then at this point, we also can introduce 2-body scattering lengths using. So you would like to introduce some lengths that will have the same dimension as that will produce dimension of energy, and from this you can establish that 2-body scattering length goes to infinity when 2-body binding energy goes to 0.
To get that kind of relation for G, do you make some ansatz for B as a function of G and then expand the Bessel functions?
Yes. Basically, what you are saying, first you're assuming that B is much smaller than G, and then you actually see that you satisfy this.
So what I mean is the right-hand side first that doesn't depend on G, only implicitly through B.
This one?
Yeah. So when you make some kind of ansatz for the
no, but from the outside, so you have a square well potential. So from outside, you actually you do not depend on G directly, but only through the binding energy.
Yes, that's what I mean. But to arrive at that relation down there, you have to make some kind of.
I assume that when G goes to 0, binding energy also goes to 0, and this.
Linear first order.
Not linear. I'm just saying that B is small. So when G is small, I'm saying that binding energy is also small, and then I actually can see that I can satisfy this equation. Okay. And so what we just learned, we learned that for a purely attractive potential, G2 is 0. And this basically means that you cannot have 3-body bound states at 2-body threshold. And this means that our simple square well potential already eliminated Efimov scenario, because you see, even though we used some particular potential, we assume that 3-body universal states, they depend only on 2-body scattering lengths, such that they actually do not depend on a shape. And if for some potential you say that you don't have Efimov scenario, then actually you don't have it for any potential. What you need to prove that or you can actually show that at the point when G2 goes to 0, you have 3-body bound states that are universal. So you have some universality involved when G2 goes to 0, and there's a number of papers that investigated this universality. And since this is workshop on universality, I would like to have a few slides about this behavior. So when two-dimensional two-body scattering length goes to infinity, or when two-body energy goes to 0, you have a three-body bound state, and for three identical particles you would have exactly 2, such that so you have two-body state and you have two three-body states with a fixed ratio between the energies. And yeah, that was first established in this paper. And now what we would like to see, we would like to, or what we'd like in this talk, what we would like to find, we would like to find another state. So these two states, they always exist, no matter what kind of potential you take, as long as two-body scattering length goes to infinity. But we would like to find such a potential that would provide us with Borromean state. So when, yeah, so sorry. Yes, sorry. Yeah, this is two-body. Yeah, this is two-body energy, and when two-body energy in some units goes to 0, three-body energy in some units goes to 0 linearly. And yeah, and so what we would like to have here, we would like to have when two-body goes to 0, you would always have these two universal states, but we would like to find such a potential that would allow us to have a Borromean state. And our picture would be changed, so when you have a weakly bound two-body state, you would have two weakly bound three-body states, but one state will be actually a compact object, and it will remain even after dissociation of two-body state.
Just anything that you don't plot this correct curve linear, but as some parabolic shape?
It's like, yeah, it's like you don't know a priori how it would look like. It's like, most probably it actually even does not feel the two-body state break. So it's like, it would, it just goes, so if you tune G linearly, it would just go linearly with G. And so basically, then it would mean that it's flat in this picture because two-body binding energy goes exponentially. Yeah? Okay, but the question is if it's possible to have such a potential that provides a Borromean state. And you can construct a few examples, and the one example that I have in mind is uses the simplest harmonic oscillator potential. So you take some potential that to a large extent or to a large radius actually reminds you harmonic oscillator potential, but then it decays at infinity fast enough such that yeah, so it decays at infinity fast enough such that it gives you a reference point, and you actually can have discrete states and continuum states. And but then approximating this potential as an oscillator, we actually can get very precisely. So by taking this peak to infinity, you can really precisely establish that two-body value for threshold will be 8 divided by some units of L, and then three-body binding energy at two-body threshold, it will be some value. And then you can also, in this simple picture, establish three-body coupling, where three-body threshold when three-body dissociate. And then you can establish as a ratio between three-body coupling and two-body coupling is 2/3 in this harmonic.
Why do you introduce the second term? I mean, the one that is proportional to
this
L?
one?
Yes.
So you need some negative, so you need your potential to be negative at least somewhere to have a bound state. So this gives you kind of an offset at 0 to provide a bound state.
So your threshold is 0, so when the two particles are far away?
Yeah, so it's like when two particles are far away, yeah, that defines your two-body threshold. And then, but you need some negative part of your potential, so you. So you need to.
Asymptotically, you go to 0 energy.
Yeah, asymptotically, you go to 0 energy, And in this way, yeah, you define a threshold energy, and then to have a bound state, you need some piece below this threshold. Okay? And it's simple to analyze this picture. And then you have three-body, you find three-body coupling that defines three-body threshold, and two-body strands that defines two-body threshold. And then you can find a ratio between those, and it would be exactly 2/3. And you can prove mathematically that it's the smallest ratio you can have. And so what does it mean? It means that if you vary strands from G3 to G2, you actually have a Borromean window where you have one Borromean state. Okay?
You still have the two universal states?
So it's like in this model, no, in this window I don't. So I have two universal states exactly when G2 at G equal to G2. You have two universal states, but you cannot capture them approximating potential only as an oscillator. So you actually need to consider, you need to consider full picture, full potential. But a Borromean state you can capture because it's actually a deeply bound object, and it sits inside, and it's actually well approximated with just a Gaussian wave function.
Is it only one state? Or?
So yeah, in harmonic, it will be only one state in using this harmonic oscillator. Yes, it will be only one state.
So can you generalize? So this all holds for this particular example.
Yes, but you can generalize it for different dimensions and for different partial waves. And you can, for example, in this way, you can, for example, prove that in 1D you can have a Borromean states for potential of such shape, in 3D also, and for spinless fermions also.
Can you have more than one state?
It's like in this picture you can't. So if you just approximate potential with, if you solve the full, you can have more, I guess. But I never seen, so I cannot rule this out. But in my all numerical examples, I've never seen two Borromean states, only one.
Even if you make L big?
So it's like you can see that here actually it's more or less independent on L. So yes, even if you make this L big, this L kind of comes only as a scale, and yes.
If you make L too big, doesn't at some point also that introduce again a two-body bound state?
Yeah, so you cannot make it too big. Yeah, you cannot make it too big. So you always you kind of try to balance between making it too big. But at the end of the day, this L comes only as a scale. So you can scale it out. For example, by putting in frequency in some particular way. Okay? So this is just a simple example that shows us that actually in 2 dimensions you can have Borromean state, but still it does not tell us a lot. And now we
Mm-hmm. Can you do this kind of the usual potential, but in the D-waves?
So it's like if you include D-waves, then it would also have some contribution here at 0. So then you actually need to be a bit more careful. But you can translate this picture, this potential, in D-waves, because with oscillators it's easy to take care of all symmetrization needed and everything.
The question is if you take a usual potential like a square well or something like that,
Mm-hmm.
and then look at it as a D-wave.
But then it would also have contribution at 0.
At 0, yeah,
You cannot. So this potential, it's not that easy to make, especially because it does not have anything at 0. So in real life, if you want for your potential to be some finite number at 0, you would rather put, for example, your particles at different layers, such that they could not directly scatter from each other. So they kind of scatter in different layers, and then you can have potential that would be of finite value at 0. But then it's not easy to make this barrier. You still can work this out, but it's not easy. Okay, and now, all the previous slides were basically for bosons, and now I would like to dedicate this slide to fermionic systems in 2D. And first of all, for two spinless fermions, you know that spinless fermions, so they can not be an S wave, so you need high partial wave, and this introduces this additional term, which what it does first, it makes the following thing. So before we could bind two spinless bosons, with attractive well of infinitely small depths. But now, when you have two spinless fermions, you need a potential attractive well of finite depths. And also, when two-body, so if you put this side to 0, you can solve the equation, because this is of short range. You can solve the equation at large distance, and then large distance behavior of your wave function would look like this. And then you can show that if you introduce another length parameter, and you can show that you can call it scattering length for p waves or whatever you like. And then if you can show that if this parameter goes to infinity, you should have a two-body bound state in this potential. And so that's for two particles. For three particles, when two-body binding energy goes to 0, or when the scattering length goes to infinity, as Sergei told us or taught us, we have super Efimov states with angular momentum plus minus 1 and energy that scales double exponentially. And as he also mentioned, this scaling holds only when n is sufficiently large. And that was first established in this paper, but also you can find information in talk by Sergei Moroz. That was preliminary. Now I would like to introduce hyperspherical formalism, because I know that not all people in this room are familiar with this, but I will be using it not heavily, but some ideas. So I will just, I have a few slides dedicated to hyperspherical formalism. So we know that, as I introduced before, our Hamiltonian looks like this. And because first what we do, we eliminate center of mass motion, because center of mass momentum is conserved. And we introduce Jacobi set of coordinates in the following way, where so when x coordinate is a coordinate between two particles, y coordinate is a coordinate that is proportional to center of mass of two particles and the third particle, and r is proportional to center of mass. Then the next coordinate transformation that you make from this Jacobi set, you make it to hyperspherical angles and hyperspherical radii. So you introduce your coordinate in this way, and then you angles phi x and phi y are the actual angles of vectors x and y in a plane, and you introduce the third angle alpha in the following way, such that alpha actually can go from 0 to pi over 2. So you introduce three angles, and they are all in finite space. So alpha goes from 0 to pi over 2, phi x from 0 to 2 pi, phi y from 0 to 2 pi, and rho goes from 0 to infinity. And in this way, you go from 4 coordinates that actually ranges over the whole space to 4 coordinates where 3 of them are actually in finite subspace. And in this way, you rewrite your Hamiltonian. So you write your Hamiltonian. First part is kinetic energy term, of course. Then you have part kinetic energy for rho. And then you would have two more terms. First, of course, is sum of your potential energy. And then, here's supposed to be G, sorry. And then you would introduce some sort of angular momentum operator, but now it will be not in, now it will be in three-dimensional space. And what we do, first we solve part with angles. So we know that potential would depend on an angle, and then this angular momentum would also depend on an angle. And we solve for a given rho, we solve for this part. And we know that because alpha phi and phi x and phi y are limited to some finite space, and these lambdas will have only discrete values. And to solve it, it's usually easier to use Fadeev decomposition and work only with, work instead of with sum, work only with one potential at a time.
What's the T sub r in the Hamiltonian?
This one? This is the kinetic energy of center of mass. So, and this part you can basically decouple. Just for consistency, I decided to keep it there. But yeah, you can just decouple because your Hamiltonian commutes with. Okay. Sir?
Could you tell a little bit more for the Fadeev decomposition?
Okay. So the basic idea is that you rewrite your wave. So in coordinate space, you rewrite your wave function as a sum of three functions, and each of these functions is in different Jacobi sets. So it's like in the first set, I directly picked my Jacobi set between two particles and a third one, but because they are identical, I can always have a channel where you have 2 and 3, and so Jacobi set between 2 and 3 and the first one. Okay, and so you rewrite your total wave function as a sum of 3, and then for each of these, so you write your wave function as a sum of 3. Yeah, psi 1 plus psi 2 plus psi 3, and then for each of these functions, you can write this equation. So when you go instead of a sum of 3 potentials to only 1 potential, and then you solve 3 equations instead of 1, but because we work with identical bosons, we can work only with one Fadeev component.
Isn't there some coupling between three different components?
Excuse me?
Should be some coupling. I mean, it doesn't.
Yeah, but it's not decoupled. So here you have still full wave function. Yeah, sorry, I had to mention. So here you still full wave function, and yeah, of course, the coupling comes from the full wave function. Okay.
So it means that for the solution of this equation, for this Fadeev component in the left-hand side, you need the full wave function in the right-hand side?
Yes. Yeah.
So for identical mass particle or identical particle, you cannot simplify, I mean, just solve for a Fadeev component.
No, you cannot solve just for one. You need to solve for other two. Yes.
But for identical particle, we can solve just for one.
Yeah, no, you basically solve for one, and the other two you get by rotations.
I mean, yeah, we can apply some permutation operators to get two other components. It means that the total wave function can be composed of one, I mean, the configuration of, suppose that we have 3 particles, I mean, I can write something here.
I can also.
Okay.
Okay.
I mean, so it means that according to Fadeev formalism,
Yeah, well,
we can call this particle 1 and 2 and 3 as an instance, so we can call this psi 3 as spectacle particle. We can have two other 1, 2, 3 again, so we can call as psi 1 because particle 1 is a spectacle, and we can also have these 2, 1, 3 that we call psi So total wave function can be composed of psi 1, psi 2, and psi 3, but it's clear that we can obtain psi 2 as a permutation P1, 3, P2, 3 over psi 1, and the same can be done here for psi 3. So I think that at the end, we can have this Fedef equation just for one of these components. I mean, psi 1,
Yeah,
or
but
it can be psi 2, or it can be psi 3. And by having these, we can,
I
I mean,
think,
that we can.
Adi, we should cut it short here. We couldn't
Yeah,
do
sure.
this more in the discussion. Let's
Mhm.
continue with this
Yeah.
now, please.
so yeah, the idea that